Good morning, students. This is Gopi Krishna, lecturer in mathematics. Today we are discussing a new unit, that is Unit 3 of 2nd BSc in the 3rd semester for the academic year 2020-21. The topic is normal subgroups. The name of the Unit 3 is normal subgroups. First of all, we learn the definition of the normal subgroup. That is, a non-empty subset H of a group G is said to be a normal subgroup of G if it satisfies the two conditions. That is, the first one is for A comma B belongs to H. That implies AB inverse belongs to H. That is, we say that this condition is H is subgroup of G. This condition is called, if the first condition is holds, then we say that H is only a subgroup of G. And the second condition is for all X belongs to G and H belongs to, that is small h belongs to capital H, that implies small x, small h, small x inverse. The product of X, H, X inverse belongs to H, then we say that H is normal. If the two conditions are satisfying for the non-empty set H, for the non-empty subset H, then we say that H is normal subgroup of group G. We can say that H is equal to 1 comma minus 1. This set is a normal subgroup of the group G is equal to 1 comma minus 1 comma I comma minus I. We know that this is the fourth roots of unity. This G is fourth roots of unity, is a group under multiplication. We know that it is clearly a group under multiplication. We learned in the first unit. If we see that H is equal to 1 comma minus 1 is a normal subgroup of that group G, we can say that H is a example for the normal subgroup of a group G with respect to multiplication, which is called fourth roots of unity. We can learn some notes from the definition of normal subgroup. We can write that for the first one is H is normal subgroup of G if and only if X, H, X inverse is contained in H for all X belongs to G. What is that? If H is normal subgroup of G, then the condition X, H, X inverse is contained in G is holds, and if the condition X, H, X inverse is contained in H, then we say that H is normal subgroup of G. Okay, H is normal subgroup of G. The second one is if G is a group, then singleton G and that means G is a group, G itself, that is G, and the singleton E, these both are called normal subgroups of group G, and these both are called trivial or improper normal subgroups. What are that? For the group G, G itself is G and the singleton E set. These two sets are called trivial or improper normal subgroups of group G. Other than these two improper normal subgroups, that means for the group G itself, that is G and singleton E, other than these two normal subgroups, all the remaining normal subgroups of this group G are called non-trivial or proper normal subgroups of group G. What is that? What are the improper normal subgroups for a group G? G itself and singleton E. These two normal subgroups are called trivial or improper normal subgroups. What are that? Improper normal subgroups. And the remaining, except these two, all the remaining normal subgroups are called proper normal subgroups of the group G. Correct? Next we learn the definition Hamilton group. That is, any non-abelian group whose every subgroup is normal is called Hamilton group. That means if we take an abelian group in that, if we take any non-abelian group, that is which is not satisfying abelian law in that group, that is called non-abelian group. A non-abelian group is said to be Hamilton group if each and every subgroup of this non-abelian group is normal. That means if a non-abelian group contains only normal subgroups, then we say that that non-abelian group is called Hamilton group. Okay, students. First of all of you want to learn these definitions very clearly. After that only we can understand the theorems. Okay, I am repeating the normal subgroup definition. That is, a non-empty subset H of a group G is said to be normal subgroup of G if for A comma B belongs to H implies A dot B inverse belongs to H. And the second one is for all X belongs to G and for all X small h belongs to capital H, that implies X small h X inverse belongs to capital H. Okay, students, a non-empty subset H of a group G is said to be normal subgroup only if it satisfies these two conditions. So if we want to prove any non-empty subset as a normal subgroup, we want to prove these two conditions. Those are for A comma B. First one is A comma B belongs to H implies A dot B inverse belongs to H. And the second one is X belongs to G and H belongs to H implies X inverse belongs to H. You can use this note also, that is H is normal subgroup of G if and only if X capital H X inverse is contained in H. If this condition is holds, then we say that H is normal subgroup. That means we can use in the further theorems. If we want to prove that H is normal subgroup, then it is enough to prove that X H X inverse is contained in H. Or if X H X inverse is contained in H, then we clearly say that H is normal subgroup. This is also can be useful, very useful note to prove further theorems. Okay, so we go to the theorem 1. What is the theorem 1? Prove that a subgroup H of a group G is normal if and only if X H X inverse is equal to H for all X belongs to G. What is that? We have to prove H is a subgroup of G is normal if and only if X H X inverse is equal to H. That means what is given for the proof? There is a common is there, that is a if and only if condition, that is necessary and sufficient condition is there. We have to prove, we have to take a G, H is normal, and we have to prove this condition X H X inverse is equal to H. In the sufficient condition, we have to take X H X inverse is equal to H, and we have to prove that H is normal. There is a common portion is there for you. It can be used for the two conditions, that is H is subgroup of group G. That's why I am writing the proof that given that H is subgroup of group G. What is the common? What is the common condition given by the statement, given in the statement? That is H is subgroup of group G. Now we are proving the necessary condition. What is that necessary condition? For that necessary condition, we have to take the LHS part and we have to prove the other part. That is, I am taking the LHS one, that is the H is normal. What is that? H is normal. What we want to prove? X H X inverse is equal to H. Now we prove that X H X inverse is equal to H for all X belongs to G. Okay, right? But from the note 1, which we are learned in the previously, that is H is normal subgroup of G implies X H X inverse is contained in H. We learned in the note 1. If you observe that, are you observing that? This is the condition. H is normal subgroup X H X inverse is contained in H. Is it right? So what that's I am using the here, that is X H H is normal. We are taking that H is normal. Okay, suppose H is normal, we have taken like that. That's why by using H is normality, that means X H X inverse is contained in H. We want to prove that X H X inverse is equal to H. So we prove that X H X inverse is contained in H. Next we prove that H is contained in X H X inverse. For that, we know that X is in G. We know that X is in G. G is a group. By inverse law, X inverse is also in G. Since H is normal and X inverse belongs to G, by using this X inverse belongs to G, the normality condition like this, for X belongs to G, H is normal, then this condition holds. But here we use it for X belongs to G. Now I am using in the place of X, X inverse belongs to G for the same condition. H is normal and x inverse belongs to G. I am replacing x with x inverse because H is normal and x inverse belongs to G. That means x replaces x inverse, H replaces H, that x inverse replaces in the x plus x inverse, the whole inverse is subset of H. Similar condition is applied for using x inverse belongs to H. Okay, this one and this one are the same. Okay, right. What happens? X inverse is as it is, H is as it is, x inverse whole inverse is x, is subset of H. I am multiplying x on the left side, x inverse on the right side, on both sides. That means this total value on the LHS part, left side multiplied by x, right side multiplied by x inverse. When we go to the right side, RHS part, left side is multiplied with x and right side multiplied with x inverse. What is in the RHS side? H. For that H, left is x, right side is x inverse. Here also left side x, right side x inverse. Now by using the associative law, what happens? X inverse is identity. Here x inverse is identity. Identity means x inverse is E into H, x inverse is E, H into E, H. The total becomes H is contained in x inverse. Let it be 2. From one, what we have learned? X inverse is contained in H, and the second one, H is contained in x inverse. From 1 and 2, we can say that x inverse is equal to H. Okay, students. Now we go to the sufficient condition. What is the sufficient? What is the necessary condition? We have taken H is normal and we proved x inverse is equal to H. Now we are going to the sufficient condition. What is that? We have to take x inverse is equal to H, and we want to prove that H is normal. That's what I am writing here is, suppose that x inverse is equal to H, we have taken this condition and we want to prove that H is normal. We know that x inverse is equal to H. X inverse equal to H means x inverse is contained in H. It is very clear. That means this condition from the note 1 we can say that H is normal subgroup of G. Okay, students. Now we proved the theorem 1. Now we go to the theorem 2. What is that? A subgroup H of a group G is normal subgroup of G. What is that? A subgroup H of a group G is normal subgroup of G if and only if each left coset of H in G is right coset of H in G. What is that? This is also if and only if. If and only if means necessary condition and sufficient conditions both are there. There is a common portion for this necessary and sufficient condition we can use. The common portion is H is subgroup of G, group G. So I am writing in the proof that given H is subgroup of group G. What we want to prove? Necessary condition. For the necessary condition, we have to take the LHS part, that is H is normal subgroup of G. Then we want to prove that this total condition, that is each left coset of H in G is right coset of H in G. That means the left coset of H is equal to the right coset of H. Okay. If you take H is normal subgroup, first of all for the necessary condition I am taking H is normal subgroup, and we prove that each left coset of H is right coset. Okay, right. For that I am taking that in the necessary condition. Suppose H is normal subgroup of G. Now we want to prove that each left coset is the right coset of H in G. We know that the condition of the normal subgroup is, since we have H is normal subgroup, that implies x inverse is equal to H by the theorem 1. Just we have learned it. Now I am multiplying right side with x on both sides. Okay, right? And you see that for x inverse, right side multiplying x, or on the right side H is multiplying with x. Okay, right? Then what happens? X inverse x becomes E. E means 1. That is xh. What remains? xh. Here right side hx. Okay, xh is equal to hx means this is left coset, this is right coset. Each left coset xh is right coset hx. Is it right? The necessary condition is over. What is the sufficient condition? We have to prove that we have to take that each left coset is right coset. Then we want to prove that H is normal subgroup of G. Okay, right. For that, I am taking that what is given that each left coset is a right coset. We have to use this condition. For that, for x belongs to G, I am taking that xh is a left coset, and hy for every y belongs to G is a right coset. Xh is equal to hy, that means left coset is equal to right coset. I am taking that left coset is equal to right coset. What we want to prove? That H is normal subgroup of G. What is that? H is normal subgroup of G. For that, we know that E belongs to H because H is subgroup. What is that H is? The common portion is there, given that H is subgroup. Subgroup means groups. Group means identity law exists. That means identity element E in H. Now, what about XE? X is X, E belongs to H. What XE? XE means X. X belongs to XH. X belongs to XH. What is the XH? What is XH? XH is equal to HY. That way, X belongs to, I replace XH with HY. That is, X belongs to HY. Then we know that A belongs to HB implies HA is equal to HB. Okay? A belongs to HB implies HA is equal to HB. Similarly, X belongs to HY means HX is equal to HY. Is it right? HX is equal to HY by using this condition. I am using this condition only. By using this condition, I am writing this like that. XH is equal to HX is equal to HY. What is HY? We know that HY means XH. I am writing that XH. I am multiplying X inverse on both sides. HX X inverse, XH X inverse. I am multiplying this total with X inverse on both sides. X inverse on right side. X inverse is E. HE is H. Okay, right. H is equal to X inverse. By the previous theorem, H is equal to X inverse means H is normal subgroup of G. Okay, students. Now we have learned two theorems. How many theorems we learned? Two theorems. Now we are going to the theorem 3. What is that? A subgroup H of a group G is normal subgroup of G if and only if the product of two left cosets of H in G is again a right coset of H in G. Means here is also we learn that if and only if condition is there. That is, here also we have necessary and sufficient condition. For the both conditions, there is a common data is given in this statement. What is that? In the proof, we can observe that common data is H is subgroup of group G. For that only in the proof I am writing that given that H is subgroup of group G. Now we are going to the necessary condition. Necessary condition means we have to take a LHS part and we have to prove the RHS part. What is if and only before part? That is H is normal subgroup of G. For that only I am taking that suppose that H is normal subgroup of group G. Okay, right. What we want to prove? The product of two right cosets of H is again a right coset of H in G. It can be applied for the left cosets also. For that only we have written here on the brackets. If we take here right, then we here also have to take right. If we take here left, then we have to take left here also. Okay, students. If we take here right, then here also we have to take right. If we here take left, then here also we have to take left. Okay, I am going to prove this theorem with the right cosets. For the necessary condition, I am taking the H is a normal subgroup of G, and we want to prove that product of two right cosets of H is again a right coset of H in G. For that, I am taking that A comma B are two elements in G, and HA and HB will be two right cosets of H in G. Now, HA into HB. What happens? I am applying associative law. AH. What is, this is a left coset. We know that if H is normal subgroup, then we say that each left coset is a right coset. So, we can convert this left coset into right coset. Left coset is AH and right coset is HA. AH replaces HA. Okay, right. Then HH into AB will become here. What is HH? If H is subgroup, we know that given that H is subgroup, H subgroup means HH replaces H. HH is equal to H. AB is as it is. That means HA into HB is equal to HAB. Product of two right cosets HA and HB is equal to HAB, which is a right coset. Therefore, the product of two right cosets is again a right coset of H in G. Similarly, we prove this theorem for the left cosets also. Correct. Now I am going to the sufficient condition. For that, we have to take product of two right cosets is a right coset, and we have to prove that H is normal subgroup. Kindly follow the cursor. Students, are you following the cursor? Correct. Suppose for that sufficient condition, I am taking that the product of two right cosets of H in G is again a right coset of H in G. We have taken that product of two right cosets is a right coset. Now we want to prove that H is normal subgroup of G. For that, I am taking that X is in G and small h is in capital H. Now I am taking that X small h X inverse. Now I am multiplying X small h X inverse with E on left side. Okay, right. What is E? E is a identity element in H. E belongs to H. Okay, kindly following the cursor. E belongs to H. Okay, H is subgroup. We know that. That's why I am writing that E is the identity belongs to H. And small x, small h, small x inverse is kind of belongs to small x, capital H X inverse. We know that this is small x H X inverse. This is only the element belongs to this element, small x H X inverse belongs to small capital H X inverse. Okay, Hx, if you understand that Hx is a right coset and another one Hx inverse is a right coset. We know that the product of two right coset is a right coset. That means Hx into Hx inverse is equal to Hxx inverse. What Xx inverse? E. He. He means H. So what we will get X H small h X inverse belongs to capital H. That means H is normal subgroup of G. Okay, students. We can similarly prove this theorem for the left cosets also. I have already told to you. These are the three theorems I have completed for today's class. So, students, I am giving you the suggestion to kindly follow the definition carefully and learn the definition thoroughly, and also the note 1. By using these two only, we have proved the theorem 1, 2 and 3. Kindly follow this one and write down the notes regularly. Okay, students? Okay, thank you.